Today we are going to discuss about the representation of floating point numbers. So we know that a floating point representation of a number has two parts. One is known as mantissa, another part is known as exponent. So when we consider a floating point number, then its first part a signed fixed point number which is known as mantissa. And the second part which designates the position of the decimal point is known as exponent. So a floating point has two parts, one is mantissa and another one is exponent. This mantissa is a signed and fixed point number part. Here the second part, exponent, represents the position of the decimal point. So if there's a floating point, number can be written as m by r. Here r is the radix. Then fixed point mantissa may be a fraction or an integer. So it has two parts, mantissa and exponent. Mantissa is a fixed point part. It may be either a fraction part or an integer. For example, here there is a decimal number is here plus 6132.789. It can be represented as a fraction and exponent. Here fraction is represented like plus 0.6132.789 plus 0 for exponent. It has two parts, one is fraction and fraction is also known as mantissa and the exponent part. So it's a fraction, it is represented, mantissa is represented as a fraction here and exponent is represented as the decimal point, position of the decimal point. So the value of the exponent indicates that the actual position of a decimal point. Here the actual position of the decimal point is 4 position to the right of the indicated decimal point in the fraction. So here fractional decimal point, the fraction decimal point is indicated here. The exponent is indicated as plus 4. That means the actual decimal point in this number or the decimal number is 4 position right, that is here. After 2 there is 4 position left to the right of the indicated decimal point in the fraction. അപ്പം നമുക്ക് ഒരു ഫ്രാക്ഷൻ കണ്ടു കഴിഞ്ഞാൽ ഇവിടെ നമുക്ക് മനസ്സിലാവും ആക്ച്വലി നമ്മുടെ നമ്പർ ഇതാണ്, പക്ഷെ നമ്മൾ ഇങ്ങനെയാണ് ആ ഫ്രാക്ഷനെയും ഡെസിമൽ എക്സ്പോണൻറ്റിനെയും റെപ്രസെൻ്റ് ചെയ്തത്. അപ്പോൾ ഇവിടെ എന്താണ് ഇതിൽ നിന്ന് ഇൻഡിക്കേറ്റ് ചെയ്യുന്നത്, പ്ലസ് 4 എന്ന് പറഞ്ഞാൽ നമ്മുടെ ആക്ച്വലി നമ്മുടെ നമ്പറിലുള്ള ഡെസിമൽ പോയിൻ്റ് എന്ന് പറഞ്ഞാൽ ഇതിൽ നിന്നും 4 പൊസിഷൻ റൈറ്റിലേക്ക് മൂവ് ചെയ്താലുള്ളതാണ് ശരിക്കുള്ള ഡെസിമൽ പോയിൻ്റ്. Then another example, if we consider a binary number plus 1001.110, it can be represented with a 8-bit fraction. Fraction is 8-bit and 6-bit exponent. Here it is 6-bit exponent and here it is represented as 8-bit fraction. So here leftmost 0, this leftmost 0 indicate that this number is a positive number. So to indicate a positive number we are use a leftmost bit is considered as a 0, and it is similar to m by 2 e, which is equal to 0.1001 into 2 raised to plus 4. Here it indicates that here this decimal point is indicated here. So 2 raised to plus 4 indicate that the actual position of the decimal point is right of the 4 position right of the this number, that is after 1001 there is a decimal point in this actual number. So floating point number also said to be normalized What is meant by normalized? If the most significant bit of the mantissa is non-zero. So here for an example, the decimal number 350. So here the MSB, what is MSB? MSB is here 3. So 3 is a non-zero value. So this number is normalized. We can say that this 350 is normalized. But assume that this is the number 00035. Here the most significant number is not 0. Sorry, is a 0. It's a non-zero, not a zero, not zero value. So this number is not normalized. Another example, when we consider a 8-bit binary number, here 000111010, this is the number. But here check the MSB. Here MSB is containing the 0. So it is not normalized because it containing 3 leading zeros. The number can be normalized by shifting 3 position to the left and discarding the leading 0. If we shift the 3 position to the left, what will be happen? The data will be 1010. So here MSB will be 1. That means it is a non-zero value. So it considered as a normalized. Then another, floating point representation increase the range of numbers that can be accommodated in a given register. So when we using a floating point number, then the storing data capacity will be increased. That is, the range of numbers that can be accommodated in the given register will be increased. Consider a computer with 48-bit words. Since one bit must be reserved for the sign, the range of the fixed integer numbers will be plus or minus 2 raised to 47 minus 1, which is approximately plus or minus 10 raised to 14. So we can, using a 48-bit word, we can store approximately plus or minus 10 raised to 14 data. A 48-bit can be used to represent a floating point number with a 36-bit for mantissa and 12-bit for exponent. So the same number can be represented as using a floating point number. In that case, 36-bit is used for mantissa and 12-bit is used for exponent. In that case, assuming the fraction representation for mantissa, if we can either use a fraction representation or integer representation for mantissa. Here we use assuming that fraction representation for mantissa and taking 2 sign bits into consideration, the range of numbers can be accommodated is plus or minus 1 minus 2 raised to minus 35 into 2 raised to 2047. That much numbers can be accommodated in that range. This number is derived from the function that containing 35 ones and an exponent of 11 bits excluding the sign bit. The fact that 2 raised to 35 minus 1, that is equal to 2 raised to 47. 2 raised to 47, 35 minus 1, that much numbers can be stored. So the mantissa can be accommodated 35 bits excluding the sign, and if considered as an integer, it can store a number as large as 2 raised to 35 minus 1. This approximately equal to 1010, which is equal to a decimal number of 10 digits. So which is very large. Then when next we are considering the arithmetic operation. What about the arithmetic operation? Floating point arithmetic operations are complex, more complicated than the fixed point numbers, and their execution take longer and require more complex hardware. So adding or subtracting two numbers require first the alignment of radix points, since the exponent part must be made equal. So first step is we need to for an addition or a subtraction or an operation, first step is we need to align the radix point, because we need to make exponent parts equal. The alignment is done by shifting one mantissa. So how to alignment is done? By shifting one mantissa while its exponent is adjusted until it is equal to the other exponent. For example, here the exponent is, consider the sum of the floating point numbers here. One is here 0.5372400 into 10 raised to 2, and here 0.15800 10 raised to minus 1. So first step is the radix point. First align the radix point, that is the exponent part must be equal. So here one is 10 raised to 2, another one is 10 raised to minus 1. So how can make it equal? One is first either shift the first number 3 position to the left. So here either shift to 3 position left, or shift the second number 3 position to the right. So either we need to shift the first number 3 position left, or the second number 3 position to the right. The shifting to the left causes a loss of most significant bits. So if we shifting the left position of the first number, then it will make a loss of most significant bit 537 like. So we need to, if we shift to the right, which causes the least losing of least significant digit. So the second method is more preferable than the previous one, because it only reduces the accuracy, while the first method may cause a error. So here we are using the second method, shift the second number to the 3 position left. So it will be added, right, then it will be added 3 zeros at the leftmost bit, rightmost bit. When 2 normalized, so it becomes 0.57. When adding these two, we will get 5373980 into 10 raised to 2. After, when two normalized mansas are added, the sum may contain an overflow digit. So, an overflow can be corrected easily by shifting the sum once to the right and incrementing the exponent. So, when an overflow occurs, then we can just shifting the sum once to the right and increment the exponent point. When two numbers are subtracted, this is all about the addition. Next we will discuss about the subtraction. If two numbers are subtracted, result may contain most significant zeros. For example, here, if we subtract these two numbers, then here's after subtraction we will get 0.00350 10 raised to 5. So most significant zeros are there. So floating point that has 0 in the most significant position of the mantissa is said to have an underflow. So this procedure, if the number, the result containing or the mantissa containing the most significant position containing the 0, then it means that After subtraction, it means that it is an underflow. So to normalize the number that contains an underflow, it is necessary to shift the Mandisa to the left and decrement the exponent until a non-zero digit appears in the first position. So what will be happen here? Here it is 0.00350. So it shifted to left. How many position? It will be shifted to 2 times. Then it will like 0.35. So this position, most significant position containing a non-zero value, so it is normalized. So in the example above, it is necessary to shift left twice to obtain 0.3500. Then 10 raised to 5, instead of 10 raised to 5, it becomes 10 raised to 3. Then next, floating point multiplication and division operation. It does not require any alignment of the Mandisa. So this product can be formed by multiplying the two Mandisas and adding the exponent. For multiplication, just multiply the Mandisa values and adding the exponent value. We will get the result. For a division operation, just dividing the Mandisa and subtracting the exponent, we will get the result. This is all about the representation of floating point number.